Hi everyone. Today we're going to be doing questions 1 and 3 from the USNCO National Chemistry Olympiad 2025 round 2. So let's start with question 1 part A. Copper 2 sulfate pentahydrate is a blue crystalline solid. Upon gentle heating, it loses water to form anhydrous copper sulfate, which is a white solid. So part A asks, when 5 grams of copper sulfate pentahydrate is heated to remove all of its water, what mass of anhydrous copper sulfate will be produced? So we know that 5 grams is equal to the total mass of the anhydrous copper sulfate and the mass of the 5 water molecules. So what do you think we can use to solve this problem? We can use the ratios of the atomic masses to find the mass of just the anhydrous, basically. So if we find the mass of the water, the 5 water molecules, we can turn it into a percent, and we can say, okay, if the water is this percent of the total mass, that means that it's also the that given percent of the 5 grams that we see. So, and we also notice that it's asking for 3 sig figs here, so that's important to note. So let's solve this. So the first step is to find the total mass of this salt, basically. So we have to look at our periodic table, and we notice that copper has a mass of 63.55 grams. Sulfur has a mass of 32.07 grams. And then oxygen is 16 grams, but there's 4, so you want to do 4 times 16. And now for the water, so this is just the anhydrous copper sulfate right here. For the water, we have 5 times, and then we have 2 hydrogens and 1 oxygen. So hydrogen is just going to be 1.01, so we can say 2.02 because it's 2 hydrogens plus the 16 from the oxygen. So the total mass should come out to be, let's do the math real quick, and again, if you need to pause the video or just wait for me to do the calculation, whichever one. Comes out to 249.720 or 72 grams per mole. So this is the total mass of the copper sulfate pentahydrate. So now we have to find what percent of that mass is the water. So our water mass is going to be 5 times 18.02, which is 90.100 grams per mole. So let's now see what percent of the water is of the total. So to do that, we can do 90.100 divided by 249.720, and we get, let's find this out, 0.36, which equals 36.1%. So that means that 36.1% of the copper sulfate pentahydrate is water. So if we now that means that let's find what percent is just the anhydrous copper sulfate. So we can say 100 minus 36.1 equals 63.9%. So 63.9% of our 5 grams is equal to the anhydrous copper sulfate. So now all we have to do is convert this into a decimal, which we get 0.639, and we multiply that times our 5 grams, and we get 3.1, around 3.2 grams, but we'll just say 3.20, we'll say to 3 decimal places, 3.196 grams per mole. Or sorry, 3.196 grams. That is our final answer right there. Alright, now that we've done problem A, let's try problem B. Explain the change in color on dehydration of copper sulfate pentahydrate. So we automatically notice that we have a transition metal, which is copper, and we have ligands. And a ligand is nothing but a molecule that can exist, or an ion that can exist by itself or attached to a transition metal center. In this case, we have 5 water molecules and just 1 copper molecule. So this will form, or we can assume that it forms, a 5-coordinate geometry, 5-coordinate complex. So it will either form your trigonal bipyramidal complex, or it will form your square pyramidal complex, which looks like this. So basically, in either of these situations, we have what's called d orbital splitting, which happens in coordination complexes. This is where the d orbitals will essentially split. So we have 5 d orbitals, your dx squared minus y squared, your dz squared, your dxy, dxz, and your dyz. So essentially, these will split into energy levels with 2 or more, depends on what energy level it is, or it depends on what complex it is, where some will be on the same level, some won't be. So in 5-coordinate geometry, the most common, I guess, outline is this splitting. So there's 2 orbitals here. There's 1 orbital here, 1 orbital here. But just for simplicity purposes, we can approximate this to an octahedral complex, which looks like this. So we have our dxy, dyz, our dxz, and our dx squared minus y squared, and our dz squared. So we can find our du electron count. Again, this isn't necessary, this is just for understanding, which is our group number of our transition metal minus our oxidation state. So in the problem, they say our oxidation state is 2. So group number for copper is 11, which I've already circled. So 11 minus 2 equals D9. So we can say that we can now fill in our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, normally you would have to determine if this is high spin or low spin. Water is an interesting ligand that it's actually on the it's on the high spin side. But because this is like a 9-coordinate complex, the high spin low spin doesn't really matter. So the important thing to note here is that we can have what are called electronic transitions, where electrons can jump between these orbitals, and this can be caused by absorbing photons, and then they release color, and that's why transition metal complexes are always super colored. So there's a few types of electronic transitions that we have to keep in mind. There's metal ligand charge transfer and ligand metal charge transfer. These both produce really vibrant colors, and they happen. Metal ligand charge transfer happens when you have essentially it's when you have ligands that when you have a metal that can donate d electrons into empty pi orbitals on the ligand. So you want to look for empty pi orbitals. So the best example that exists is the carbonyl ligand, where there's 2 empty pi orbitals. This is what we call a pi acceptor ligand, actually. For ligand metal charge transfer, we have what are called pi donor ligands, which donate electrons into empty d orbitals on the transition metal. So for these, we have the most common examples are chloride, bromide, and iodide. And we don't see these here. Why? Because water is not a strong metal ligand charge transfer ligand, or it's not a strong pi donor or pi acceptor ligand. So the only one left, the only, I guess, transition that we have to worry about is what are called D to D transitions. So these are what we call Laporte forbidden transitions, which states that you can't have transitions between 2 d orbitals, but this is always broken, or it's very commonly broken because of symmetry. It's a bit more complicated than that, but just remember these are very commonly broken. So D to D transitions occur when you have d orbitals that are not completely filled. So you can see this is a half-filled orbital. And we can say that this electron right here can actually jump to this orbital and back down. Any of these can, actually. The important thing is that the spin stays the same. You can't have it jump up and the spin changes. But because we can jump up and down, we can say that D to D transitions can happen. So now we know why our copper sulfate pentahydrate is colored. But we have to understand that it's asking, explain the change of color on the dehydration. So when the water is removed, you no longer have this coordination complex. Coordination complexes only happen when you have ligands and a transition metal. And when your ligands are getting removed, now you only have a sulfate ion. Now, sulfate can't act as a ligand. So because of that, we can assume that the change in color on dehydration to, in the problem, where does it say? It forms a white solid, so essentially a non-colored solid. We can say that our answer is the color essentially goes away because there are no longer ligands which are the water molecules to provide and complete D to D electronic transitions. So that's our answer. I'll just show that one more time. Quick note, if you want to ace your next chemistry or science exam, compete at the highest level, or even place first in national chemistry or physics Olympiads, I highly recommend checking out Chempra.academy. Chempra isn't just another study site, it's a training ground. You get carefully designed, world-class practice problems, step-by-step solution breakdowns, and content that actually teaches you how to think through complex STEM problems, not just memorize formulas. Whether you're preparing for Olympiads, AP and college exams, or you just want the best practice questions available anywhere on the planet, Chempra.academy gives you the depth, rigor, and structure serious chem students need to stand out. All right, so let's try part C. A solution of a 0.0506 gram of copper acetate, copper 2 acetate hydrate is made up with water to a volume of 5 milliliters of water. The solution is a 1 centimeter cuvette. In a 1 centimeter cuvette produces the visible spectrum shown. What wavelength should be the best choice to determine the concentration of copper 2? So this goes back to our Beer-Lambert law that you might have learned in Gen Chem if you have taken general chemistry. So basically, we can say that the law states that our absorption is equal to our epsilon constant times our max wavelength times your cuvette length, basically. So we can say that your absorption is always proportional to your maximum wavelength. This is, by the way, your molar absorptivity constant, just to be more specific. So that means that to find to most accurately determine the concentration of the copper salt, we need to find when this wavelength is at its maximum. So just looking at the graph here, we can see that the maximum is right here, which if we trace down to here is approximately 760 nanometers. So that's our answer for that one.